Hello, my name is Jezreel and I will be discussing trapezoidal rule, Simpson's rule, and integration with unequal segments that's under the numerical differentiation and integration, specifically under the Newton codes formula. Motivation. We all know that calculus is the mathematics of change and is an essential tool to the engineers since engineers must continuously deal with systems and processes that changes. So in calculus, if you still can remember, we have differentiation and integration, right? So to begin, let's start with the differentiation. To differentiate means to mark off by the differences. Distinguish, to perceive the difference in or between. Mathematically, the derivative, which serves as the fundamental vehicle for differentiation, represents the rate of change of a dependent variable with respect to an independent variable. So as depicted in the figure shown, the mathematical definition of the derivative begins with a difference approximation. One common form of the difference approximation is the finite difference method that is shown here. So if delta x is allowed to approach 0, as occurs in moving from A to C, the difference becomes a derivative, where dy over dx, which can also be designated as y prime or f prime xi, is the first derivative of y with respect to x. As seen in the figure, the derivative is the slope of the tangent to the curve at xi. Right. The second derivative represents the derivative of the first derivative. And the second derivative tells us how fast the slope is changing. It is commonly referred to as the curvature. When we have high value of second derivative, it means that we have high curvature. And finally, partial derivatives. Partial derivatives are used for functions that depend on more than one variable. Partial derivative can be thought as of taking the derivative of the function at a point with all but one variable held constant. So for example, given a function f that depends on both x and y, the partial derivative of f with respect to x at an arbitrary point xy is defined as this. And similarly, the partial derivative of f with respect to y is defined as this. Since we have done with differentiation, we will now proceed with the integration. We all know that the inverse process to differentiation in calculus is integration. So according to the dictionary, to integrate means to bring together as parts into a whole, to unite, to indicate the total amount. Mathematically, integration is represented by this equation, which stands for the integral of the function of x with respect to the independent variable x, which stands for the integral of the function fx with respect to the independent variable x, evaluated from a to b. As suggested in the dictionary definition, the meaning of this equation is the total or the summation of f of x over the range a and b. So the figure represents the graphical manifestation of the concept. For functions lying above the x-axis, the integral expressed in this equation corresponds to the area under the curve of f of x between a and b. As outlined above, the marking of or discrimination of differentiation and the bringing together of integration are closely linked processes that are in fact inversely related, that can be seen in this figure. So for example, if you are given a function yt that specifies an object's position as a function of time, differentiation provides a means to determine the velocity. Conversely, if we are provided with a velocity as a function of time, integration can be used to determine the object's position. It can be seen here. Thus, we can make the general claim that the evaluation of the integral is equivalent to solving the differential equation for yb, given the initial condition ya is equal to 0. Non-computer methods for different differentiation and integration. The function to be differentiated or integrated will be typically one of the following three forms. So first is the simple continuous function such as polynomial, an exponential, or a trigonometric function. Second, a complicated continuous function that is difficult or impossible to differentiate or integrate directly. Third, a tabulated function where values of x and f of x are given at a number of discrete points, as is often the case with experimental or field data. In the first case, the derivative or integral of a simple function may be evaluated analytically using calculus. For the second case, analytical solutions are often impractical and sometimes impossible to obtain. In these instances, as well as the third case of discrete data, approximate methods must be employed. A non-computer method for determining derivatives from data is what we call equal area graphical differentiation. In this method, the xy data are tabulated, and for each interval, a simple divided difference delta y over delta x is employed to estimate the slope. Is a simple divided difference of delta y over delta x is employed to estimate the slope. Then these values are plotted as the step curve versus x that can be seen in this figure. Next is a smooth curve is drawn. So this is the curve that attempts to approximate the area under the step curve. That is, it is drawn so that visually the positive and the negative area are balanced. The rates at given values of x can be read from the curve. In the same way, visually oriented approaches were employed to integrate tabulated data and complicated function in the pre-computer era. A simple intuitive approach is to plot the function on a grid, then count the numbers of boxes that approximate the area. This number multiplied by the area of each box provides a rough estimation of the total area under the curve. This estimate can be refined at the expense of additional effort by using a finer grid. Another common sense approach is to divide the area into vertical segments or stripes like this, with a height equal to the function value at the midpoint of each strip. The areas of the rectangles can then be calculated and summed to estimate the total area. In this approach, it is assumed that the value at the midpoint provides a valid approximation of the average height of the function for each strip. As with the grid method, refined estimates are possible by using more and thinner strips to approximate the integral. For differentiation, the most fundamental numerical techniques use finite divided difference to estimate derivatives. For data with error, an alternative approach is to fit a smooth curve to those data with a technique such as least squares regression, and then differentiate this curve to obtain derivative estimates. In a similar spirit, the numerical integration or the quadrature methods are available to obtain integrals. These methods are actually easier to implement than those grid approach we had earlier. That is, function heights are multiplied by strip widths and summed to estimate the integral. However, Through clever choices of weighting factors, the resulting estimate can be made more accurate than that from the simple strip method. In the simple strip method, numerical integration and differentiation techniques utilize data at discrete points. Because tabulated form is already in such a form, it is unnaturally compatible with many of the numerical approaches. Although continuous functions are not originally in discrete form, it is usually a simple proposition to use the given equation to generate the table of values. As shown in this figure, the values from the table can then be evaluated with the numerical method. So A, we have here a complicated and continuous function, and B has a discrete values of f of x generated, of course, from the function. And C, in here, we use the numerical method or the strip method to estimate the integral on the basis of the discrete points, basis of these points. So, meaning we no longer use, meaning letter A is unnecessary. Numerical differentiation and integration in engineering. Differentiation is a commonplace in engineering because so much of our work involves characterizing the changes of variables both in space and time. In fact, many of the laws and other generalizations that figure so prominently in our work are based on the predictable ways in which change manifests itself in the physical world. So a prime example is the Newton's second law, which is not couched in terms of the position of an object, but rather in terms of its change of position with respect to time. Aside from such temporal examples, numerous laws governing spatial behaviors of variables are expressed in terms of derivatives. Among the most of these are the laws involving potentials and gradients. So for example, Fourier's law of heat conduction. It quantifies the observation that the heat flow is from high to low temperature. And the one-dimensional case can be expressed mathematically as this. Heat flux is equal to negative k prime dt over dx. Thus, the derivative provides a measure of the intensity of the temperature change, or gradient, that drives the transfer of heat. Similar laws provide workable models in many other areas of engineering, including the modeling of fluid mechanics, mass transfer, chemical reaction kinetics, and electromagnetic flux. The ability to accurately estimate derivatives is an important facet of our capability to work effectively in this area. Just as accurate estimates of derivatives are important in engineering, the calculations of integrals is equally valuable. A number of examples relate directly to the idea of the integral as the area under a curve. So this figure shows a few cases where integration is used for this purpose. So as you can see, this letter A, a surveyor might need to know the area of field bounded by a meandering stream and two roads. B, a water resource engineer might need to know the cross-sectional area of a river. And C, a structural engineer might need to determine the net force due to a non-uniform wind blowing against the side of the skyscraper. These are the examples of how integration is used to evaluate areas in engineering applications. A common application also is to determine the mean of a continuous function. In part 5, we were introduced to the concept of the mean of n discrete data points. So please recall the equation 5.1, P 5.1. Please recall equation PT 5.1, where yi are individual measurements. The determination of the mean of the discrete points is shown in this figure. So these are the discrete points. discrete data and this is the continuous data. In contrast, suppose that y is a continuous function of an independent variable x that is shown in this figure. So for this case, there are an infinite number of values between a and b, just as in equation PT63. So can be applied to determine the mean. You might also be interested in computing the mean or average of the continuous function y is equal to f of x for the interval from a to b. Integration is used for this purpose as is specified by the formula. This formula has hundreds of engineering applications. For example, it is used to calculate the center of gravity of irregular objects in mechanical and civil engineering and to determine the root mean square current in electrical engineering. Integrals are also employed by engineers to evaluate the total amount or quantity of a given physical variable. The integral may be evaluated over a line, an area, or a volume. For example, the total mass of a chemical contained in a reactor is given as a product of concentration of chemical and the reactor volume, or where concentration has units of mass per volume. However, suppose that concentration varies from location to location within the reactor. In this case, it is necessary to sum the products of local concentrations, Ci, and the corresponding elemental volumes, delta Vi. So the mass is equal to the summation of Ci times the delta of Vi from 1 to n, where n is the number of discrete volumes. For the continuous case where C, x, y, z is a known function and x, y, z are independent variables designating position in Cartesian coordinates, integration can be used for the same purpose. So this is the triple integral, which is referred to as the volume integral. So notice the strong analogy between the summation and the integration. Another example, the total rate of energy transfer across a plane where the flux in calories per square centimeter per second is a function of position is given by which referred to as an areal integral, where A is equal to area. So the heat transfer is double integral of flux dA. Similarly, where A is the area. So this is the formula. And similarly, the one-dimensional case, the total mass of variable density rod with a constant cross-sectional area is given by M is equal to A integral of rho x dx from 0 to L, where M is the total weight, L is the length of the rod, rho x is the known density, that is kilograms per cubic meter, as a function of length xm, and A is the cross-sectional area of the rod. Now let's go to the mathematical background. In high school or during our first year in college, we were introduced to differential integral calculus. There, we learned the techniques to obtain both analytical and exact derivatives and integrals. So when we differentiate the function analytically, we generate a second function that can be used to compute the derivative for different values of the independent variable. Rules are available for this purpose. So for example, in this case of a monomial, that is y is equal to x to the power of n. So once we differentiate it, it will become dy over dx is equal to n x to the power of n minus 1, where n must not be equal to 0. So which is the expression of the more general rule form. Y is equal to u to the power of n, where u is a function. Its derivative is equal to dy over dx is equal to n u to the power of n minus 1 du dx. The two other formulas apply to the products and the quotients of functions. So for example, product of two functions of x, u and v, is represented as y is equal to uv. Then the derivative can be computed as dy over dx is equal to u dv over dx plus v du. On the other hand, if we have the quotient, y is equal to u over v, then its derivative is equal to dy over dx is equal to v du over dy over dx is equal to v du over dx minus u dv dx over v squared. And in this figure, or this table, shows us the commonly used derivative. This is the trigonometric function. Similar formulas are available for definite integration, which deals with determining an integral between specified limits. So as in integral of, or as in integral between specified limits. Integral between specified limits. I is equal to the integral of f of x dx from a to b. According to the fundamental theorem of integral calculus, this form will become this form, where f of x is the integral of fx, that is any function such that f prime x is equal to fx. The nomenclature that's on the right side, or this one, simply means fb minus fa. The example of a definite integral is this one. So this case is the function of a simple polynomial. It's a function of a simple polynomial that can be integrated analytically by evaluating each term according to the rule. So we'll be using this one. This is the general rule for the integration, and just substitute each one. So once we substitute all these, we will have the value of I is equal to 1.640533. This value is equal to the area under the original polynomial between 0 to 0.8. Here are some integrals that can be used in part 6. The a and b in this table are constant and should not be confused with the limits of integration discussed in the text. So I think this is familiar with you guys, since you have encountered this on your college days. Now we'll discuss the Newton Cotes integration formula. 3 of the most widely used Newton Cotes formula are discussed in detail. So the trapezoidal rule, which I will be reporting, the Simpson's 1/3 rule and Simpson's 3/8 rule will be discussed by co-reporter. All these formula are designed for cases where the data to be integrated are evenly spaced. In addition, we also included in the discussion of numerical integration for unequally spaced data. This is a very important topic because many world applications deal with data that are in this form. All the above materials relates to close integration. So where the function values at the ends of the limits of integration are known. All the above materials are in close integration, meaning all the functions of the limits are known. So the trapezoidal rule, the Simpson's 1/3 rule, and Simpson's 3/8 rule. To begin, the Newton Cotes formula are most common numerical integration schemes. They are based on the strategy of replacing a complicated function or tabulated data with an approximating function that is easy to integrate. So this is the general form, where f of n, x is a polynomial form, and n is the number of polynomial. In this figure, we can see that there are 2 different lines. In figure 21.1a, this is what we call the first order polynomial, or the straight line. This is used in the approximation, while on this one, we used the parabola. Well, on letter B, we used the parabola for the same purpose. The integrals can also be approximated using a series of polynomials applied piecewise to the function or data over segment of constant length. So for example, in figure 21.2, three segments rather are used to approximate the integral. Higher order polynomials can be utilized for the same purpose. Closed and open forms of the Newton-Cotes formulas are available. The closed forms are those where the data points at the beginning and end of the limit integrations are known. So this is the closed point. So the first and the last, or the end limits, are known. On the other hand, the open forms have integration limits that extend beyond the range of the data. So as you can see, there is no known points at the end of the data. So these two are what we call the closed and the open integration formulas. Open Newton-Cotes formulas are not generally used for definite integration. However, they are utilized for evaluating improper integrals and for the solution of ordinary differential equations. This chapter emphasizes the closed forms. However, material on open Newton-Cotes formula is briefly introduced at the end of this chapter. Now let's start with the trapezoidal rule. The trapezoidal rule is a numerical integration technique used to approximate the definite integral of a function over a given interval. It is one of the simplest methods for approximating integrals and is based on approximating the area under the curve by dividing it into trapezoids and summing their areas. The trapezoidal rule is mostly used in the numerical analysis process. The trapezoidal rule is the first of the Newton-Cotes closed integration formula. It corresponds to the case where the polynomial in I is equal to integral of fx dx from a to b is approximately equal to the integral of fnx dx from a to b is first order. So we just changed the letter n to first order, so it's 1. Recall that a straight line can be represented as this one. So f1x is equal to fa plus fb minus fa over b minus a quantity x minus a, which is a linear interpolation formula. So from this one, that is f1x is equal to fx naught plus fx1 minus fx naught over x1 minus x naught quantity x1 minus x naught. The result of the integration is the area under the straight line is an estimate of the integral of f of x between limits a and b. So this one. And this becomes this, that is equal to I is equal to quantity b minus a, fa plus fb over 2. And this is what we call the trapezoidal rule. How were we able to get to the trapezoidal rule? This is the derivation of the trapezoidal rule. Before the integration of this equation can be expressed as this one. So we just xfb, xfa over b, and f of a is at the middle part. So grouping the two terms, so this one, we'll just group this, so we will have this result. And if you can see, this one will be AFA plus AFA will be cancelled out. So it will leave us with this equation, which can now be integrated between x, which is equal to a, which can be integrated between x is equal to a and x is equal to b, that yield to this equation. Right. So once we substitute and evaluate, this will give us this equation as well. We know for the fact that b squared minus a squared is just equal to quantity b minus a, quantity b plus a. So substitute this squared, so this will cancel out. This will cancel out. So what's left is I is equal to bracket fb minus fa, b plus a over 2 plus bfa minus afb. So multiplying and collecting the same terms will yield us to this equation, which is the formula for the trapezoidal rule. Geometrically, the trapezoidal rule is equivalent to approximating the area of the trapezoid under the straight line connecting FA and FB. Recall from geometry that the formula for computing the area of a trapezoid is height times the average of the bases. This one. But in our case, the concept is the same, but the trapezoid is on its side, here. Therefore, the integral estimate can be represented as I is approximately equal to width times the average height, or quantity b minus a times the average height, where for the trapezoid rule, the average height is the average of the function values at the endpoints, or fa plus fb over 2. All the Newton codes closed formula can be expressed in this formula. I is approximately equal to b minus a times average height. The errors of the trapezoidal rule. When we employ the integral under the straight line segment to approximate the integral under a curve, we obviously can incur an error that may be substantial. An estimate for the local truncation error of a single application of the trapezoid rule is 12 f double prime she b minus a q, where she lies somewhere in the interval from a to b. The equation above indicates that if the function being integrated is linear, the result from the trapezoidal rule will be exact. Otherwise, the function with second and higher order derivatives, that is with curvature, some error can occur. This is the graphical representation of the use of a single application of the trapezoidal rule to approximate the integral of this function from 0 to 0.8. How do we derive the trapezoidal rule as well as the error estimates? So going back, an alternative derivation for the trapezoidal rule is possible by integrating the forward Newton-Gregory interpolating polynomial. Recall that for the first order version with an error term, the integral would be like on the box 18.2. So this becomes I is equal to the integral of fa plus delta fa alpha plus f double prime she over 2 alpha quantity a minus 1 h squared bracket dx from a to b. So to simplify the analysis, realize that because alpha is equal to x minus ah, so dx is equal to h alpha, inasmuch as h is equal to b minus a for one segment trapezoidal rule, the limits of integration a and b corresponds to 0 and 1 respectively. Therefore, this equation can be expressed in this equation. So I is equal to h integral of fa plus del sine of fa alpha plus f double prime she over 2 alpha quantity alpha minus 1 times h squared d alpha from 0 to 1. So if it is assumed that the small h, the term f double prime she, is approximately constant, then this equation can be integrated. So from this, it will be evaluated to this. That is, I is equal to h bracket f a plus delta fa over 2 minus 1 over 12 f double prime she h cubed. Because delta fa is equal to fb minus fa, then the result can be written as h fa plus fb over 2 minus 1 over 12 f double prime she h cubed. Thus, the first term is the trapezoidal rule and the second term is the approximation error. So example, this is the single application of the trapezoidal rule. So the problem statement is, use equation 21.3 to numerically integrate this function from a, which is equal to 0, to b, which is equal to 0.8, and recall that in section and recall from section PT 6.2 that the exact value of the integral can be determined analytically by which is equal to 1.640533. So the function values are, when f is equal to 0, let's go back here. So when f is equal to 0, it will have 0.2. When f is equal to 0.8, then substitute 0.8 to all x's and we get the value of f of x that is equal to 0.232. We can now substitute these values to the formula we had earlier, that is I is equal to approximately equal to 0.8, 0.2 plus 0.23 over 2, which is equal to 0.1728, which represents an error of 1.467733 from 1.640533 minus the one that we got, that is 0.1728, which corresponds to a relative error of 89.5. The reason for this large error is evident from the graphical depiction of the figure 21.6. Notice that the area under the straight line neglects a significant portion of the integral lying above the line. In actual situations, we would have no foreknowledge of the true value. Therefore, an approximation error estimate is required. So to obtain this estimate, the function's second derivative over the interval can be computed in differentiating the original function twice. So the second derivative is equal to negative 400 plus 400 or 1050x minus 18800x squared plus 8000x cubed. So doing the average of the second derivative, this will give us negative 60. This will give us negative 60, which can now be substituted to yield our EA is equal to negative 112 negative 60 times 0.8 quantity to the power of 3, which gives us 2.56, which is the same order of magnitude and sign of the true error. A discrepancy does exist because of the fact that the interval of this size, the average second derivative, is not necessarily an accurate approximation of f double prime she. Thus, we denote that the error is approximate by using the notation EA rather than using ET. So we'll now proceed with the multiple application of trapezoidal rule. One way to improve the accuracy of the trapezoidal rule is to divide the integration interval from A to B into a number of segments and apply the method of each segment. So the areas of individual segments can be added to yield the integral for the entire interval, which results to the equation called the multiple application or composite integration formula. So from 2 segments, this becomes 3 segments, 4 1, 2, 3, 4 segments, 5 segments. This is an example of a multiple application trapezoidal rule. Here at letter A, we have 2 segments. Letter B, we have 3 segments, 1, 2, 3. And on letter C, we have 4 segments. 4 segments, that's 1, 2, 3, 4, and for letter D, we have 5 segments. This figure 28.1 shows the general format and the nomenclature we will use to characterize the multiple application integrals. There are n plus 1 equally spaced base points x0, x1, x2 to xn, and consequently there are n segments of the equal width. So h is equal to b minus a over n. If a and b are designated as x0 and xn respectively, the total integral can be represented as this. Then substituting trapezoidal rule for each integral yields this equation. Then we will group this equation. So if you can see, we have a common here. So we can group this equation. This becomes I is equal to h over 2 fx naught plus 2 summation of xi plus fxn from 1 to n minus 1. And we know for the fact that h is equal to b minus a over n. So substitute this h to this h. This will give us this result. So 2 to n b minus a. Because the summation of the coefficient of f of x in the numerator divided by 2n is equal to 1, the average height represents a weighted average of the function values. According to the above equation, the interior points are given twice the weight of the two endpoints. That's fx0 and fxn. An error for the multiple application trapezoidal rule can be obtained by summing an individual errors for each segment to give this error. So where f double prime xi is the second derivative at a point of xi located in segment I. This result can be simplified by estimating the mean or the average value of the second derivative for the entire interval. So this will result to this. So therefore, the summation of f double prime xi is approximately equal to n f double prime. And the equation et is equal to negative quantity b minus a cube over 12n cube summation of f double prime xi when I is equal to 1 to n can be rewritten as this. So that's EA is equal to negative b minus a cube over 12n squared f bar double prime. Thus, if the number segment is doubled, it means that the truncation error will be quartered. An example of a multiple application trapezoidal rule. So the problem statement. Use the two segments of trapezoidal rule to estimate the integral of this equation. I think this is just the same as the example we had earlier from a, which is equal to 0, and b, which is equal to 0.8. Employing the equation 21.13 to estimate the error. Recall the correct value of the integral, that is 1.640533. So we know for the fact that there are two segments for n is equal to 2 and h is equal to 0.4. So let's have the value f naught is equal to 0.2, f 0.4 is equal to 2.456, and f 0.8 is equal to 0.232. So in substituting all these values to the equation, this will give us I is equal to 1.0688. And the ET is equal to 0.57173. That comes from subtracting 1.640533 minus 1.0688. This will give us 34.9%, and our EA is equal to 0.64, where negative 60 is the average second derivative determined by our previous example. So the result for the multi-application trapezoidal rule to estimate the integral of the given function, where x is equal to 0 to 0.8 and the exact value is 1.640533. So you noticed that the error decreases as the number of segment increases. However, also notice that the rate of decrease is gradual. This is because the error is inversely proportional to the square of n. So this is this one, the square of n. Therefore, Doubling the number of segments quarters the error. Now, we will proceed with the computer algorithm for the trapezoidal rule. So there are two simple algorithms for the trapezoidal rule. These are the single segment version and the multiple segment version with constant width. And this is the program. So in A, you will see the single segment version, and on letter B, this is the multiple segment version. So example 21.3, evaluating integrals with a computer. The problem statement is use a software based on figure 21.9b to solve the problem related to our friend, the falling parachutist. As you recall from example 1.1, the velocity of the parachutist is given as the following function of time. So this is the velocity of our parachutist. That's Vt is equal to Gm over C quantity 1 minus e to the power of negative C over m quantity t, where v is the velocity, that is in meter per second, g is the gravitational constant, that's 9.8 meter per second squared, m is the mass of the parachutist, which is equal to 68.1 kilogram, and c is the drag coefficient. The model predicts the velocity of the parachutist as a function of time, as described in example 1.1. Suppose we would like to know how far the parachutist has fallen after a certain time t. This distance is given by this equation, where d is the distance in meters, and we will substitute this equation to the given formula as a function of time. So d is equal to gm over c, integral of 1 minus e to the power of negative quantity c over m t dt from 0 to t. Use your software to determine this integral with a multiple segment trapezoidal rule, using different numbers of segments. Note that performing the integration analytically and substituting known parameter values result in an exact value of d is equal to 289.43515 meters. And here is our solution. So for the case where n is equal to 10 segments, a calculated integral of 288.749 is obtained. Thus, we have evaluated, for the case where n is equal to 10 segments, a calculated integral of 288.7491 is obtained. Thus, we have evaluated the integral of 3 significant digits of accuracy. The results for other numbers of segments can be readily generated. So, up to 500 segments, the multiple application trapezoidal rule attains excellent accuracy. However, notice how the error changes sign and begins to increase in absolute value beyond 500 segment. So the 10,000 segment case actually seems to be diverging from the true value. So this is due to the intrusion of the round of error because of the great number of computation for these many segments. Thus, the level of precision is limited, and we would never reach the exact value of 289.4351 that was obtained analytically. So there are 3 major conclusions that can be drawn from the example. First, for individual applications with nicely behaved functions, the multiple segment trapezoidal rule is at just fine for attaining the type of accuracy required in many engineering applications. Second, if high accuracy is required, the multiple segment trapezoidal rule demands a great deal of computational effort. Although this effort may be negligible for a single application, it could be very important when a numerous integrals are being evaluated. Or B, where the function itself is time-consuming to evaluate. For such cases, more efficient approaches like those in the remainder of the chapter and the next may be necessary. Finally, round of errors can limit the ability to determine integrals. This is due both to the machine precision as well as the numerous computations involved in simple techniques like the multiple segment trapezoidal rule. Thank you very much for listening. Once again, this is Jess, and my reference for this report is the Numerical Methods for Engineers 8th edition by Steven Chopra and Raymond Canale.